Yeah. I need to mute myself or no? It's fine. Okay, cool. Yeah, so good afternoon, everyone. Good morning if there's someone online. So yeah, my name is Yuguang. Thanks, Professor Chassis, to introduce myself. So as mentioned, I actually doing the job for the NTU, not just for research, but also try to attract the young scholars to join NTU. That's why I will spend some time to kind of introduce NTU. So basically, this is one of the kind of global hub. I mean, for Singapore, basically, Singapore is a very nice place, and everyone, if you visit that, there's a very beautiful city and a lot of kind of places that we can have fun, and yeah, a couple of things here. And for NTU, so this is it started from 1955 as the Nanyang University. So far, we renamed as the Nanyang Technology University, starting from 1991. As I think this is one of the top young universities in the world. So civil engineering basically is one of the three founding school in NTU. So here's more kind of information about what is the College of Engineering. So we have 9,000 undergraduate students, 4,500 graduate students. We have 5 engineering schools, and we have quite a diverse kind of faculties from different countries. And this is kind of more details about each school and the kind of research is doing. And regarding funding parts, I think this is also one of the attractive points to move into Singapore, because there are so many, and the government is very generous to dedicate money for the research, and there are also quite a few very so many kind of collaborators to contribute not just income but also the cash for the projects. And regarding the global ranking, this is the top number 2 for the engineering for US News, and for QS ranking, this is number 11. For THE is about 14. And this is some additional ranking for civil engineering is about 9. Yeah, I think we keep that for a couple of years. It's just a floating back and forth. Yeah. So, and this is the dean, Warren Chen. I think he's a very energetic and also very open-minded to attract more people from worldwide to join NTU. And thank you for your attention. So if you are interested, please send email, and also you can also let me know. In the meantime, we are also organizing the Young Scholar Forum that actually doesn't need to be kind of dedicated to join NTU as objective, but it's actually an opportunity to have some experience kind of traveling around Singapore for free, because the NTU will cover all the fees, and it's the invite-only activity. So, okay, cool. So that's just the 7 minutes. Okay. Any questions? If you can also ask me.
And can I suggest maybe after the end of your seminar, if it would be nice if you meet the group members so they can approach you and you learn something about them, or you discuss about options for visiting.
Yeah, okay. Okay, let's move on to the main component for the research. Yeah, so here's my research topic: edge intelligence for structured health monitoring system developments and benefits in applications. So as Professor Chassis mentioned, I'm a sensor guy. Basically, I spent quite two years in PhD to learning all the electrical engineering, computer engineering, and then after that, we are developing IoT sensors, and eventually to commercialize that as part of the company's products to sell for different universities and also the different countries as well. So today, I will talk about my continuous efforts in this area. So this is backgrounds about what I'm going to do. Especially I focus on edge intelligence because this is actually a kind of a future direction for structural health monitoring. Basically, we try to push the AI computing to the edge devices. Basically, it's edge computing plus artificial intelligence, and then we pick up the words in the top and the button. So that's why it's called edge intelligence. So and these days, because of the kind of fast development in the edge devices like NVIDIA and a lot of new chips and growing very fast, so it make this area very vibrant and very promising. Okay, so now let's go back to the background. We always talking about the infrastructure is aging, especially for the United States. I spent 7 years there. When we talk about PhD study, the proposal application, we all talk about the AEC infrastructure reporting card, right? So it's usually talking about there's some of the buildings actually built after World War II, and a lot of things we need to fix. In the meantime, since I'm currently living in Singapore, Southeast Asia, the population growing very fast. So that's actually is a burden on top of the existing infrastructure. The thirdly, there's also a risk about the earthquakes, the impacts, or some other kind of man-made hazard that actually have caused the additional stress on the infrastructure. Here's a little bit more about the Singapore side. We have around 205,000 buildings. Yeah, most of them actually 30 years old. And we also have several kind of accident happenings recently in the last 5 years. For MRT tunnels, this is basically the subway system. We also have the similar similar situation. Yeah, we had a couple of accidents happening in the last 2 years. That was a lot of downtime cost. And for sewers also have the similar situation. So, and SHM can help us, basically structural health monitoring. So when we talk about structural health monitoring, we talk about some dam detection, we talk about structural health monitoring system. From my background, more focused on structural health monitoring systems. We need sensors, we need to deploy the system for continuous and a long time to collect the data, to do condition assessments. And initially we do the wire for the maybe 20 years ago, even 30 years ago. And I think most representative example is the Qingma Bridge in Hong Kong. And there are, I think, over 300 sensors channels deployed there. And but that case, it's not easy to kind of scale up to different bridges. This is just one of the significant structures in Hong Kong, but there are so many bridges, right? Can we expand that for kind of maybe tens of thousands of bridges to have similar setup? So then people think about, okay, can we move to the wireless? So wireless basically we remove wires. It's easy for installation. You don't need to remove the wires. If you have experience for a lab test, you'll be kind of frustrating about how to kind of make the wires well organized, right? So it's actually quite challenging part for wires. That's why we go with wireless. So wireless basically we need to address the power, because wire usually to the power supply. We need to address the data transmission. That's the other challenge we need to address. So the most representative example is the Jingdu Bridge. So this actually for long-term monitoring about over 100 sensors. That times IMO2. And it's a low cost, is for easy installation. Yeah. So this is my PhD work. I just walked with one slide to summarize. This is XNO, which is basically the product in my PhD advisors company. And we sell quite a few to different countries. My job is try to develop the first of all is to develop the operating system. It's called FOSS. Real-time operating system. So that's actually quite challenging for resource constrained edge devices. I also try to develop the trigger sensing circuit. So instead of we doing the duty cycling, I'm not sure if anyone knows what is duty cycling. Basically, it's try to save energy because you cannot turn on the sensor continuously using battery, right? To save time, to save the power, you should put the sensor go to deep sleep, and then wake up and a deep sleep. So this duty cycle to save energy. But in that case, we were missed the event like earthquakes or Golden Gate Bridge. There's 1 year deployment, but missed 3 earthquakes. So that's actually a challenge. Because duty cycle. That's actually yeah. So that's why we're motivated to develop trigger sensing. Basically, if there's some event of interest like earthquake or impacts happenings, you can wake up and then turn on the data collection afterwards. And yes, I also wanted to clarify, I also want to emphasize that our work also get the support from SBIR as about small business innovation research. A small money, about 225K, but it's encouraging us to moving forward. So for this case, we're actually doing more about the bridge impact detection because there's so many overhead bridge moving across the railway bridge. And in that case, this type of accident may happens without notice or get reported after a couple of hours. So we want to do the timely detection for that. Okay, so this is some of my backgrounds. Now keep moving forward. Since we have so many IoT technologies, and also AI going very fast these days, so we are trying to think about what would be the revolution coming to our SHM system. Right? So the first thing we think about is the decentralized system. So traditional ways we do the centralized. We collect the sensor data, go to the base station or to the cloud server, and then we process data, and then that we're kind of dealing with the data inundation, right? Or big data challenge, right? So, and also there's also issue for data transmission parts. If you have too many channels, like 300 channel, 400 channel, then the data transmission will be delayed. So since we can have more power for edge devices and also IoT technology, so we can actually push some of the work from the cloud server to the edge device. That's why we say decentralized, okay? So I think decentralized is a kind of a common word, so buzzword these days, right? So like blockchain and also other things, right? So similar to we can also do that in the SHM system as well. And now the other thing here is, since we can kind of move some tasks to the edge devices, can we move the AI to the edge devices? That's actually the question we're thinking about. So edge intelligence, as I mentioned, is the combination AI and edge computing. And most representative example is the drones inspection. So because drone will take a lot of photos, and the photo is actually very heavy, large volume. If you transmit back to the cloud server and do the post sensing analysis, there will be a lot of delay and also very heavy to do the process. So that's why many people they do the job. They try to push the computer in the drone itself. Okay, so drone take a photo, drone processing the data, and drone send back the information, not the raw image, but the information. Basically, information say, okay, there's a crack. What kind of crack happening? Or what is the dimension of crack? For that case, the information volume will be squeezed a lot or compressed a lot. Okay, so this is actually one example. A very hot topic in this area. So for me, I'm not working on drone, but I'm working on IoT sensors. So that's why we are going to the other kind of direction is called AIoT. So this is also another buzzword, AI plus IoT. So this could be the sensors could be some kind of small controllers in the smart home system, right? Or part of the kind of a transportation or vehicle system. But this actually could be some small sensors. Okay. And what we're doing here is we try to push not just the edge inference. Basically, you train the AI in the server and then try to do the inference in the edge devices. We also try to push the training in the edge as well. So in that case, we need to address more challenge. So the challenge here, we listed several in terms of the limited resource for the onboard computing, the network latency, the constrained power supply, and lack of tools and libraries. Yeah. And also I would like to clarify, we are even pushing further. So for NVIDIA, Jetson, so this is Jetson, very powerful kind of edge devices. This is still power hungry. You still need a very big battery or more power to supply for continuous processing. We actually push into the microcontroller, not just a microprocessor. Microcontroller, for example, Arduino. Arduino is microcontroller. I'm not sure if some of you already play with that. Okay. So it's actually very limited resource, but for sure it could be a more consistent or sustainable for long-term operation. And also we try to address the domain-specific applications, which is differentiated from other companies' job. All right, so here's the summary. What we are going to do. We try to realize edge intelligence for structural health monitoring in the system, such that we can provide early warning of hazards like bridge impact, like explosion, like earthquakes, and capture the high fidelity transit vibration response. Like impact, it could be 2 seconds, right? Very short duration. How can we capture the data without any data loss? We can perform onboard structural anomaly assessments for informed decision making. So there always have the questions why we should bring edge intelligence. What is the benefit of edge intelligence? So here I summarize here is that because of edge intelligence, we can upgrade in low cost to be more powerful, right? Usually low cost the sensor is actually cheap, chip, and but functionality would be compromised, right? If you compare with the very bulky seismic sensor, very big one deployed in some area, and but if you can just use Arduino MEM sensor to replace that, for sure we can. That's possible as long as we have AI technology to equip with the sensor. So that's the one example. The other one, we can reduce the number of sensors, right? So if the one sensor is more powerful, when the number of sensors can be reduced for the single building, and also we can scale up the deployment because instead of the centralized data collection analysis, we can have decentralized, meaning that each cluster of the sensor network can deal with their job independently, right? So we can scale up easily. So here's the three benefits of the edge intelligence that bring to the structural health monitoring system. In summary, for the industrial collaborator, basically that's actually try to save the money, right? Reduce the cost. That makes them happy. Okay, so smarter, scalable, and accessible. I will talk something about more sensor part. Sure. So this is still ongoing. We play with the ESP32 and the STM32. We still working on that. You see a lot of bunch of jumper wires. I mean, it looks like a little bit messy because we still try to optimize the hardware setup. Basically, there are main control, the perception part, the interaction part, communication part, and the power part. Okay. So here's a list of the table. A list of components related to the model size and also specifications. For example, the microcontroller part, the memory part, the accelerometer, the camera, the Bluetooth, Wi-Fi, and also a screen as well. So regarding the middleware, there's a hardware is called TinyML, tiny machine learning, because that actually is suitable for edge computing parts. Ours, we actually do in similar way, but we try to make it more domain specific for tiny structural health monitoring, which will be including several math calculation, the digital signal processing, and also AI technology related to structural health monitoring, such that. So the purpose for that is that we try to develop a middleware service such that other researcher in the community, they can directly build upon this middleware server without doing their job to building from the scratch. And so that can save their time to do the edge intelligence analysis. Basically in our, I'm not sure if any of you participate the Hong Kong, the APS summer school, Anquist conference, not really, right? Yeah, so at that time I also present something, and the most interesting part is that we bring the sensor. We actually purchased each component from Taobao and only 300 RMB for everything, and then we led them to do the hands-on practice. We're starting from the assembly for each components and do the programming, and eventually they have their box of the sensor to deploy on the pedestrian bridge to do the model analysis. So that's actually quite exciting, I believe, for the students. Yeah. So I tried. So this is just an example to say, okay, we try to kind of build the scaffolding for people to reduce the gap for these direction analysis, these directions research. Okay. All right. So before the sensor part, we are also doing something about. Now let's move on to the edge intelligence. Right? What edge intelligence can help us? The first thing what I would like to do is I want to develop smart sensing, smart IoT sensing. What is smart? the first example, the trigger sensing, as I mentioned, I tried to address the challenge facing by monitoring system in the Golden Gate Bridge. Okay, so this is the more kind of currently more advanced framework compared with my PhD study. We try to formulate the entire system as the control loop, and the basic objective try to sorry, maybe I should summarize what is the control, what is the triggering look like. So the idea is simple: is that if the we have the Sentinel sensor at low cost, very low fidelity data, but it's actually keep tracking of the vibration of the bridge. Okay, and if the vibration exceeding the threshold, then that's actually the indication of the trigger. Okay, and we use that parameter to wake up the sensor and then do the condition assessment afterwards. That's the basic idea. So there are two parameters we need to define or hyperparameter. One is the threshold vibration. The second is the continuous duration for that exceeding threshold duration of time. Okay, so there's two parameters, but these two parameters actually very difficult to set, especially for different structure. They have different condition scenarios. Yeah. So what we try to do is we use these control loops such that we can optimize. So the kernel here is the Bayesian optimization. Try to optimize these two parameters based on the limit observation of the measurement data we reserve. Okay. And the objective tries to improve the F beta index. Okay. So this is one example. So when the trend will cross, that's in the North America. That's actually we have the sensor turn on quickly, and after the trend will just go away, then there's no vibration, and the sensor will be turned on. So we're seeing the dashed line is the wire sensor for continuous monitoring as the baseline or reference, and then the blue one is the wire sensor for trigger sensing demonstration. Yeah. So the other thing here is the sensor for diagnosis, which is also part of smart sensing challenge we should address, because when we deploy sensor, there's always a concern that sensor is actually has shorter lifetime compared with the building, right? So that's actually one of the concern for industrial people to adopt wireless smart sensor. So we try to address in two ways. First of all, we try to kind of do data anomaly detection. And later on, we try to do the fault diagnosis. We try to identify what is the real issue behind the phenomenon of the anomaly data. And then everything can be formulated by the AI model. So this model is actually trying to do the classification of different phenomena or different data anomaly, like drift, fires, and for example, and spike, for example. Yeah. So the figure on the right hand side shows, below is actually the one of the kind of data anomaly happening look like. It could be the spike, could be the drifts, or could be the combination. So here is actually the location where we have this jump of the signal. Okay, this is actually not this is actually malfunction of the sensor. Okay, and the way to address that, we keep track of the features and we try to classify what sensor behave. In that case, we can do subsequent remediation or repair or recover strategy accordingly. Yeah, so the way to kind of identify classification and choose the best strategy is we let AI to do the job. So this is we train AI model starting from the very simple pattern recognition neural network, MMT, multi-layer perception. And the things that accuracy is not going up again after we make the network more and more complicated. So x-axis is the model size and presents the complication of the model. On the other hand, we do we're starting with very complex like Google Net neural network. So very high fidelity accuracy of the classification, but we try to kind of reduce the model size such that it can fit well with the resource constraint as devices. So we do the compression, the pruning, the et cetera, et cetera. So eventually it's actually still not able to kind of achieve high accuracy, small model size. That's actually the ideal Plato that we are. So my student doing some kind of knowledge distillation besides and also some additional kind of encoder feature selection strategy, such that we can go to this actually this is an early data point. We can have high accuracy and a low model size. Yeah, figure on the bottom shows after we identify the type of the data force, then we can do the recovery based on signal processing. Eventually, we can get the good data afterwards. So everything we put in the sensor itself. In that case, we can make sure that data coming from the sensor is always safe. It's always a good and high quality. Yeah. So in that case, it's also part of smart sensing. Yeah. Thirdly, is the data imputation and prediction. Is that there are sometimes we were missing data. This is also another concern for the sensor deployments. And so data imputation or data prediction is a very common task. For this is one of the examples that people are working on, like using convolution neural network or LSTM, long short term machine learning technology. But if you look at the most of the people working on the time history domain, if you look at the accuracy, target is blue, the prediction is the red. It's matched quite well. If you plot the error, it's still quite small. But if you plot in the frequency domain, especially the dB scale, we find that the peak value matches very well. But for the remaining, the rest of the area is actually not quite doing well. So our objective try to do not just the time history prediction performance is good, but also we want to achieve the frequency domain prediction accuracy is also good. In that case, we can do more comprehensive jobs based leveraging the frequency information. So our idea is simple. Is that before I move on, this issue is actually part of the is actually a common issue challenge for the AI or deep learning is for spectral bias. Spectral bias is that basically AIs can do a good job for low frequency curve fitting, but for high frequency it's difficult, right? So our job is basically idea is very intuitive. Is that if the problem is complex, why we just decompose the problem into several simple tasks and let the AI to learn task by task, right? So in that case, we can actually can do a good job for that. So for example, for these peaks, we have 1, 2, 3, 4, 5, or 6 peaks. So the task is we decompose the signal into 1, 2, 3, 4, 5, 6 components. Each component have 1 peak, okay? And then AI can just learn 1 peak very easy, okay? So that's actually the signal decomposition. We use the VND as the technology, okay? And after that, we just do the simply combination of the signal. But in that case, there's still kind of residual components for off-peak frequency energy. So the way to address that, we use the bandpass filtering. Kind of we do some further kind of cutting for the signal, such that we can have more clear combination afterwards. So this is the result. If you compare the top one, the bottom one, you see that not just even the time domain part, our area is even compressed or squeezed, and the frequency domain we find that is doing a much better job for the matching for the between the ground truth and also the prediction. Yeah. So this is another aspect for the smart IoT sensing. Why it is smart? Okay. In that case, we can do further more accurate or higher fidelity for data acquisition. So the lastly is the saturation. Okay, saturation is also a very common issue when we deploy sensor, especially for railway tracks, right? If the train move across, we're generating a lot of big peaks, and that could easily saturate the exceeding the measurement range. Okay, so if exceeding that, then the signal become quite messy. Yeah. You can also use the high peak or high G sensor. High G sensor basically is actually higher measurement range, but the fidelity is low because the ADC is the same. You know ADC, right? Analog to digital converter. Basically, we try to kind of chunk the signal into multiple pieces. And in that case, you can convert the continuous signal to the digitalized or discretized signal. Sorry, I guess I talked too much about the signal when I learned 2 years of my PhD. So the basic idea is that, okay, let me just make it easy to understand. Okay, so to avoid signal saturation, industrial people need to spend more money to buy more powerful sensor with high fidelity and a bigger measurement range. Okay, so our idea is that can we use the low cost sensor with the low measurement range that can do the job that expensive sensor can do. Okay, so that's actually the power for the edge intelligence to reduce the cost but do the same task. Okay, so we this is the AI technology trying to do the autoencoder, and then we actually, I think we do some kind of domain transformation. Eventually, we can actually achieve the peak value match very well with the traditional ground truth value, such that we can actually avoid or we can recover the signal saturation. Okay. All right, so this is about the IoT part. Yeah, so this is basically the uniqueness in my research group. Yeah, because many people in SHM, they deal with the data directly from sensor. They purchase sensor from a company, use the data for subsequent analysis, either by the signal identification or then detection or even risk analysis. So our parts, we push that part even further. So if we can address the sensor, then we can make bigger impact because everyone will use the sensor. If the data is good, then the result will be much better. So the next task is that what does edge intelligence can help for the subsequent applications, especially for structural anomaly detection. Yeah. So this part could be maybe more related to most of the researchers in the community. Okay. Anomaly detection basically is I think this is also a kind of a interesting or hot topic these days. Basically, especially we have the unsupervised learning autoencoder happening or developing these days. There's anomaly. Basically, we set the threshold of the normal condition, and if the signal say there's something wrong, then we can pick up that anomaly then to send a warning message to the bridge owners. Yeah. So one example is the interstellar drift. Right. So how we kind of when the earthquake happening, right? So how do we quickly identify which building require more manpower to do the inspection? We cannot send people building by building, right? So it's very time consuming, right? Especially when there earthquake happening in the big city. So the idea is actually simple: is that we just keep tracking of the drift of the building for each floor. If the drift ratio between each floor is actually smaller, I think the value well recognized in the committee is about 0.1%. Then the building is good. Otherwise, building has some damage. If exceeding 1%, that means there's severe damage. Then we should send people to do the inspection. So this is actually kind of one common index that can help engineer to prioritize the building inspection for after the earthquake happens. Okay. So this building is actually in San Francisco, and this figure is actually coming from ATC 1997. I just borrowed the figure for the illustration. On the other hand, we can also use the displacement for lateral condition assessment for the timber trestle bridge in North America. Everyone knows that in North America, there's so many rural area bridges, and most of the bridges actually looks very old, especially for the timber trestle. So the idea is that if the train move across, the bridge will vibrate vertically, maybe not quite significant, but horizontally it will move a lot. Okay. So how do we use the horizontal or transverse movements to identify the structure condition or bridge condition? Yeah, so that's actually I think a useful index, especially when the train moving across. Okay, so that's why based on this kind of observation, displacement is a good index for the community, for the engineers to better understand or visualize or imagine the bridge conditions or building conditions. Then we are doing the job is that can we just use the single sensor to provide this information, right? So displacement sensor is actually difficult because you need the reference, right? But displacement, if for LVDT, you need the reference point, and then you just measure the 2-point relative movements. So our idea is that can we just use a single accelerometer to do the job? So so that's why we are doing the kind of filter design, right? So acceleration, if you want to convert to the displacement, you need to double integration. Acceleration to velocity integration one time, velocity to displacement integration twice, right? But there's a could be challenge about the noise accumulation because of the integration. So the way to address that, we use the high pass filter. It basically bypass the low frequency error, and also doing the integration twice concurrently with this FIR filter. Okay? And on the right hand side, I showed the comparison between the displacement, ground truth, and also displace prediction using acceleration meter. So accelerometer, yeah. And if after basically build upon that, then we can actually do interstory drift. So idea is that we can have the sensor for each consecutive floors, and then we can calculate the relative acceleration using the same filter such that we can estimate the drift between each floors. Okay. So, and then based on that, the drift, we can actually set different thresholds to determine if the structure is in good condition or bad condition for fast condition assessments. Yeah. And so far, everything is in the computer. So our target is the edge intelligence, right? So edge intelligence, basically, we want to move everything to the edge. Okay, so that's why we do a couple of different experiments to move this calculation to the microcontroller devices. So the main question is, can we make it faster? Because the microcontroller is very slow, very small memory. So if we do the same job with the computer, then for sure it will take longer time, and accuracy will be also compromised. So here's the different things about we use different digital signal processing and also filtering strategies such that we can speed up the process. I think the increase the ratio is about, I think times about 87 times, yeah. And this eventually we can do real time processing, real time conversion from acceleration to the displacements, yeah. And here's the deployments. We use the 6-story building model with some X node on top of that for the displacement estimation, and then the camera for the computer vision based reference displacement measurements. And on the left hand side is the comparison. They measure quite well. Yeah. So this is for the building. We're also moving a little bit more for the bridge, right? So if can we do the same thing for the bridge displacement based condition assessments? Yeah. So in this case, we actually introduce we actually explore to usage of the Gaussian process regression modeling. So the idea is that we put the sensor for the pier of the bridge. So usually for timber trussel bridge, if you look at if you look at this bridge, we have two pier plans. Very for each pier, we have one sensor on top of that, and when the train will cross, the bridge will vibrate horizontally, and using that horizontal deformation of one pier corresponding to the other pier for these two, assuming that they have their correlation when the train will cross. So if the bridge is in good condition, their correlation should be within some certain value or certain range. But if the structure has some damage, for example, if we reduce the stiffness of this pier, then their correlation is actually will change, right? So the idea is think about their relationship and use that information when each train move across, we can collect one data set, and then we pick up the maximum displacement as a single point on the figure here. And then based on this data figure, we can actually build the Gaussian process regression model, right? And then we can actually use the statistic process control to analyze how sensitive it is to keep tracking of the damage. So on the x-axis is the strength reduction ratio, and y-axis the residual value between the estimation and also the the model prediction. Yeah. Okay, so so this is actually illustration about how sensitive it is. So it looks like is good. And the next step is how do we move it to the edge? Again, we always think about edge intelligence. First, you can reduce the cost and scale of the deployments. So the idea is simple: is that we actually put let each sensor do to the displacement estimation using the FI filter to the double integration and high pass filter concurrently. And then for each sensor, after do the displacement estimation, we pick up the maximum displacement, sending back to the gateway node. And in the gateway node side, once we collect the data points from each sensor nodes, then we can build this Gaussian process regression model and also statistical process control testing. And with that, the model will be sitting in the gateway node and do the condition assessments continuously. So the next thing is that if we deploy that, we want to see what is the accuracy, or is there any compromise the accuracy will drop because of these deployments. There's a comparison. We have ground truth is in the red dots, and the prediction by PC is in purple, and the prediction by sensor is in the cross mark. It looks like this. Although there's some difference between ground truth, but between PC and sensor they match quite well. On the right hand side, similar for the statistical process control anomaly detection, we also get very consistent results. Okay, so this is the first anomaly detection based on the displacement. We also try to explore the signal processing for anomaly detection. Yeah, if you look at the figure on the left hand side, assuming we have the sensor for continuous high fidelity, no noise measurements, then we can get these very smooth measurements. Okay, if there's some damage happens, then the signal will jump. Okay, that's what we call signal discontinuity. This kind of intuitive, right? But the thing is that if the noise increase, then this sudden jump will be submerged. So we will see that there's no this type of observation happening. Okay, so then people use the wave transform. After the wave transform, we can have some components, this type of spike signal, to represent the happening of the damage. Okay, represent this type of signal jump. If we further increase the noise level, even though you do the wave transform compare left and right, you will find that this spike actually become very, very difficult to observe. Okay, so then to further extract this kind of signal indicator, discontinuity indicator, then we can use the blind source separation. Here we use the ICA, I think important component analysis. Yeah, ICA. Okay. So for ICA part is the idea is that if we have this type of spike signal with the source signal, we mix them together. If we do independent component analysis, we can further reverse back and find this type of the signal. This is called blind source separation. Yeah. So and we do examination for this strategy. We find that there's also still a limitation about the noise level. Everything is about noise. Okay? If noise further increase, this type of strategy become less effective. And so that's why we try to quantify the signal to noise ratio, SNR. SNR is small, meaning that the noise level is high. Sorry, yeah, noise level is high. And you'll find that for weighted transform, after we introduce noise, then the number or successful rate for the spike-like signal detection will drop. That's why we see the drop in from right hand side to left hand side. If we have the weighted transform plus ICA with basically blind source separation, it do a little bit good job, a better job for the which is green line here. Okay? But we will further drop it for the SNR increase to 30. And then our strategy, we try to introduce additional signal decomposition layer before we transform. In that case, we can pulling up the successful rates, even though the SNR is actually reduced to 30. Yeah, so this is actually one improvement for this strategy based on signal discontinuity based anomaly detection. The other thing we want to explore is that because this type of the spike signal, for the traditional method blind source separation, we heavily rely on human eyes. We try to use the human eyes to see, is this really interesting source or not? Is this an interesting source? Is this an interesting source? We rely on human to do the determination or judgment. This actually not quite autonomous and also could be not easy to scale up. That's why we introduced the shape-plate transform. Shape-plate transform, basically we try to kind of explore different type of the shape of the signal, and using AI try to kind of mapping for different pattern of shape corresponding to interesting source or not interesting source. The figure on the right hand side is actually shows some example of the interesting source related to the damage information. Yeah, so you use that, we can actually automate the process of the blind source separation or signal or structural anomaly detection. And here's an illustration in terms of the numerical strategy. And on the top side shows without VMD with a high noise level, you will find there's no spike signal interesting source. But if we with the VMD, you'll find that IC1 still have this type of spike signal, quite obvious. Okay. And if you look at the right hand side showing the location of damage, so the new strategy actually can still doing a good job, which is the blue, the black one as identification of the damage in third floor, but the red one is that traditional one made a mistake in terms of the number of the floor for damage. And here's the after we introduce the shape-plate transform for continuous condition assessments based on the detection score. Okay, and figure here shows the number of floor of damage and also the damage time as well. Okay. And here's the actual lab test setup, because for sudden damage it's not easy to emulate. That's why we introduced the electric magnet. Yes. So the electric magnet meaning that if we cut off the circuits, then the connection here will be broken, right? Such broken will kind of emulates the sudden damage of this board. And on the right hand side, the signal we observed, we collected, and then ground truth that we have the 20% damage detection, damage reduction, stiffness reduction at that board. If you look at the signal, you'll find there's no such type of signal jump. But if we use our strategy, you'll find the IC2 represents the interesting source, and it can tell you around 11 seconds we have this type of the signal. And we can also use the weight of this type of IC components to identify which floor has the damage. Here we showed number 4 floor has the damage. Yeah. So, and here's the kind of streamlined process using shape-plate transform. I will just skip that. Okay, so last section of slides talk about full-scale applications. Yeah, I hope that's more interesting. For the first application is the railway bridge condition assessments. Yeah, so as I mentioned, for North America, there's so many rural area railway bridges, okay, and this bridge is actually quite simple, but it's difficult to deploy sensor everywhere. And here is one example of a steel bridge, and we put the sensor. We would do some pilot tests to see if our edge intelligence strategy can help to address the problem, especially for the feasibility of long-term deployments. And we deploy some sensors, leaf node on the deck, and also we have gateway node here. This is train will cross. On the right hand side, showing that based on our trigger sensing, how many trains we capture within the certain days of the deployments. And we can classify the train even into passenger train and also the freight train. Freight train basically has a longer duration. So this is one observation we have. And also we test their feasibility in terms of long-term deployments. And one simple index is the battery level, right? Can our battery be sustainable for the over 1 month deployments? And here's the voltage change over the time. Since we have the solar panel, you can easily see that the signal actually maintain a voltage level, maintain a certain level without big jump. There's some big jump here, because of the cloudy or raining conditions. Okay, but still the structure is survival for the continuous condition assessments. Okay. And then we move on to the real structure for scale out deployments. Here's this total, I think, 10 bridges and deployments. And this is the bridge look like. You'll see that it's quite old, right? Timber trestle bridge. And similar to what I mentioned, for each pier, we deploy one sensor on top of it and try to monitor their lateral displacements of these bridges, of these piers. And for each train will cross, so for each train move across, we can keep track. We can measure their acceleration and then convert to the displacement. Okay, so the figure on top is the lateral displacement. Here's the vertical displacement, and here's the temperature. Here is actually another observation that this deformation is actually highly relevant to the temperature change. So we can actually do some additional signal processing, try to excluding the temperature effects. Okay, and then here shows how we do the Gaussian process regression model. Each data point represents one train moving crossing events, and then x-axis is the one pier maximum displacement, and the y-axis the other pier maximum displacement. And then here's the kind of data plotting or accumulation, and eventually we can build this type of the Gaussian process regression model. And for new data sets coming in, we can actually first check if it is within this kind of safe range. If yes, then we can further fine tune this model. Otherwise, we can do kind of this type of the statistic process control to identify the data points exceeding the thresholds. And then based on the statistic analysis of how many data points exceeding the thresholds, we can actually create this type of the figure, classify the bridge into green, yellow, and red, indicating the severity of the bridge damage condition in the timber trestle bridge. On the right hand side, showing the percentage of the yellow data points collected for the over 1 month deployments of the different bridges. Okay, so this is for timber trestle. We're also doing steel bridge deployments. Okay, so here's the one steel bridge. Here's another steel bridge. Okay. We do the same thing. We collect the acceleration. We do the displacement estimation. The interesting thing that for this bridge, which should correspond to the second one, we will find that one side lateral displacement is much bigger than the other sides, indicating there's some damage happening for that side of the bridge. Okay, and on the right hand side, showing compare with their inspection report. There's a match in terms of the reduction of the cross section due to the erosion, matching well with our findings of the continuous assessments. Okay. And the second application is about the railway track anomaly detection. So this one we still dealing with the train crossing events monitoring, but we more focus on the track defects, including fastener failure, wheel flats, and also rail corrugation. Yeah, so this is actually become more and more critical in Singapore, where there's so many accident happens because of this type of the faults. Okay, so here's the deployment of sensor. We put the fiber optic sensor around 1 kilometer for the Bukit Panjang MRT turnouts, and we also deploy the IoT sensor in several locations to collect the acceleration. And here's the kind of illustration about how do we do the fiber deployments and also the accelerometer deployments as well. Okay. And here we also use the trigger sensing strategy, meaning that when the train will cross, we wake up sensor system with the data collection. Okay. In total, we can capture around 200 train crossing events per day for 24 hours.
Professor, would you like to summarize so we have also time for a short question?
Oh, sorry. Yeah,
sure.
Yeah, okay. Let me just quickly go through. Yeah, so this is the wheel flat detection. Is about we using the this train crossing event collection data for AI to do the training and classification. Here's the finding, identify the where's the when we find the wheel flags, and also report to the company. We also try to do the cross-model transfer learning. Basically, we try to do the limited acceleration measurements, and then to transfer that knowledge to the continuous distributed fiber optic sensing or measurements data. So we can improve the accuracy from 94 to 98 because of that transfer learning effects. We also do the real defects. Here is actually try to address the challenge about we have limited labeling data in the massive data collection, and how do we use the semi-supervised learning try to improve the accuracy. Lastly, slides actually showing me how do we use the this type of anomaly detection further to realize the predictive maintenance. Basically, we use this index change over the time to tell the owners to see how far is the damage or deterioration of the track away from the real good condition. Yeah, so this is a good, bad, and this good going back until here. We replace the new track and then the index going down. Okay, so this is actually a very good example to tell you how can we use this anomaly detection to enable predictive maintenance. Okay, so lastly, I would like just to do the conclusion. I introduced the AIoT prototype, which actually especially to support edge intelligence. And edge intelligence is very helpful to reduce the cost, scale up the deployments. The first application is about how do we make the sensing smart, okay? In terms of the trigger sensing, for diagnose, data importation, sensor saturation recovery, such that we can upgrade the low-cost sensor to be more powerful. And the second edge intelligence application aspect is the structural anomaly detection, such that we can scale up the deployments for less efforts, for minimum efforts. And lastly, I talked about two full-scale applications, including railway bridge monitoring and rail track monitoring. One is in North America, one is in Singapore. Thank you for attention. Okay, for 1 hour, sorry. That